I hope you're all full of energy because we're going to talk about energy and power systems for the next hour. In particular, applications of mixed integer nonlinear optimization in power systems. And then I will try to talk about advanced optimization in power systems. So I'll give you an introduction into power grid applications and try to derive the power flow equations and then formulate one problem, that's the optimal power flow problem, that's a very famous problem, and show some other problems that are related to it. So the power grid in the United States is really, really large. There's about 100,000 lines or edges. There's probably many more now. This is a map of all the generating power plants. And again, this is sometime in the 90s. There's many more now because, in fact, this is 2005. But there's many more now because we have renewable energy. So in the Midwest, we're building wind power plants. Over here in Colorado and New Mexico, we're building very large concentrating solar power plants. So that adds to this complexity. Some of the projects that we've done with colleagues at Argonne is look at modeling concentrating solar power plants. So those are those plants where you have a tower in the center and you have mirrors, a large array of mirrors all around it that concentrate the sunlight on the top of this tower. At the top of the tower, the temperature reaches something like 800 Fahrenheit. So that's really, really hot. And you have a circular pump that pumps salt, molten salt, through through the power, and then has a turbine that with water that then at a heat exchanger that then generate power. We've done some contingency analysis as bi-level optimization games. We looked at NOx permit markets. So there are interesting conclusions you can make where if you have a market for example, CO2 emissions or other emissions, players can sort of buy off these permits and drive up the cost of generation for their competitors because they then have to use more expensive cleaner energy. The integration of uncertain wind generation is something that colleagues of mine have done at Argonne. Mitigation of cascading failures. If you have interconnected systems and part of the system fails, how do you respond to it? The scheduling of black start generators is really interesting. So that's a problem where the power grid has been down, and now to restart the grid is actually a really difficult operation. And there are some generators which can restart from scratch. Other generators actually need power on the lines before they can come back up. And then very recently we looked at geomagnetic induced current blockers. So if there are solar storms, depending on the direction and intensity, when a solar storm hits the surface of the Earth, it generates a magnetic field. And it's not dangerous to humans, but what happens is whenever you have a magnetic field and you have a copper wire across that magnetic field, it induces a current. And this current can actually bring down the power grid. So there have been examples of some of these solar storms that have actually sort of hampered some of the generation in Canada. So lots of really interesting applications. The equations are kind of difficult. So this is a little bit, I'll try to do a good job of introducing them. The power flow equations are equations that happen on a network. So here's a very rough, very small, or very coarse network that sort of includes Alabama, Georgia, and South Carolina. It's a very small example, EPRI 21. And there's a sort of physical network that you can think of on your map. And connected to it is a sort of schematic representation of this network in terms of where the generators are and where there is demand in the network. The definition of the network is we have a set of buses or nodes. That is the terminology that electrical engineers use, and a set of lines or edges. And the nodes or buses are denoted by N, and the lines by L. And there is a line if two buses are connected by a power line. That's the definition of a line. Connected to this power grid is the to the topology is then also the physical properties of the power grid. So there is something called the network admittance matrix, and this is a complex n by n matrix. So there is an entry for every pair or potentially a pair of buses, and you can rewrite this matrix Y as in Cartesian coordinates or rectangular coordinates as G plus JB. So G and B are real matrices, and J is the square root of -1. So the modeling here will be done in complex variables. But we can always go from complex variables back to real variables by, for example, doing a rectangular coordinates or by working in polar coordinates, where we look at the magnitude of Y and then the phase angles e to the j phi. The voltages are called voltage phasors. So those are, again, complex variables. There's a voltage phasor, or one complex voltage variable per node or per bus. And we can again write those in polar or rectangular coordinates. And I'm using D and Q for the power or for the voltages in these cases. There's also a current injection phasor that's again modeled with, you can model this again with a polar or Cartesian coordinates. And there's one caveat here, that if we use angles, then the whole system is invariant to actually a constant degree change throughout the system. So if I add 90 degrees to the whole system, nothing changes. And this is sometimes fixed by picking one particular node or one particular bus and fixing the angle on that bus. So all angles are then with respect to this reference bus. There are two different kinds of formulations that you can make for the power flow injection. So the first one is a sort of balancing equation between the power injection I at the node I and the voltages at all the other nodes Vk. And the relationship is through this admittance matrix Y. And then and you can then also substitute equation, the left equation of 1 into the right equation of 1, and if you do that, you get this slightly more compact representation. So this representation here is effectively the right-hand equation that you have there, but instead of I just substituted the complex conjugate in there, and if you do the conjugation, you get these values here. So the over bar is the complex conjugate of a complex number. So in rectangular coordinates, that's Vd minus J Vq, for example. And then you have this additional constraint, the squared voltage magnitude. Okay, so there are two main types. There's actually three types of power flow equations. You can either formulate them in rectangular or polar coordinates. So I'm going to show you both of these formulations. And so they're given here. I have a better formulation in a moment that I'll show you. That's actually a little bit nicer. So the variables here are the voltages V and the active and reactive power at the nodes I on the left-hand side. And so those are balancing equations, and the B's and the G's are constant matrices that correspond to the rectangular coordinates of your admittance matrix. And then the voltage squared magnitude is just given by this simple formula that you know that the square of the magnitude is equal to the square of the real plus the square of the imaginary part of your of your complex variable. And you can write those down. It's fairly simple calculus. The polar flow equations look slightly different. I should point out there's something that is kind of important. There's these variables QIK and PIK that will play an important role, and they're called line flows. So on each line that is connected to node I, there's a flow that's described by this equation here. And those are the flows that go across the lines, and we will have constraints on the magnitude of these flows, because if there's too much flow on a line, then the lines can overheat, for example, and the power system would break. So then there's a similar equation, set of equations if you go and do the same thing in polar coordinates. So those are these two equations. Again, you can look at the slides later. What I wanted to show is this optimal power flow problem. So the goal here is to, given the power system network and admittance matrices and all the constants that we have, we would like to minimize the cost of power generation. And the cost is usually a function of the injection at the generators. So GI and GI are generator nodes. And in these equations, if there is no generator at node I, then these would just be absent. So I'm just doing a little bit of shorthand notation here. But there's a cost of generation that we want to minimize. We have constraints on the type of generation that we can do. There's an active and reactive power generation limits. And then there are limits on the voltages and on the difference between the angles, the phase angles. So this is in polar coordinates now. And then we have the two power flow equations, and then the line flow limits. So those are limits on the flow along the lines. And the variables are here indicated in blue. So the thing to look at is that this is really not a very easy problem. So f is maybe a simple function. It's sometimes a simple quadratic function. So that's relatively easy to model. But the remainder of the system, especially the power flow equations, are really look quite difficult. So you have multilinear terms here that involve the magnitudes of VI, VK, and cosine of the angle differences. And so this is generally a non-convex, nonlinear optimization problem. So this is kind of the bread and butter problem that people who work in power grids would look at, the AC, alternating current, optimal power flow problem, AC OPF. And so this is a very famous problem that lots of people work on, and it has some interesting expansions. So one extension is to load shedding. So you have your generation and you have demand, which I haven't introduced yet, at some of the nodes, and you may not be able to meet the demand. So one question then is, can you tell some of your consumers to reduce their demand? And you do this by introducing slack and surplus variables. So Ti plus are sort of imaginary parts of the surplus variable, Si plus are the real part of the surplus variables. And so this allows me to play around with the demand at certain nodes, and I can now, for example, ask my customers to reduce their demand, for example, by solving this problem. So I now minimize the cost of generation plus the penalty of not meeting the demand. So if I'm asking you to not use electricity, then I'm going to have to pay you something, right? You want to, I don't know, you want to go on your PlayStation or Zoom your parents, and you can't do it if you don't have electricity. So I'm going to have to pay you for not using electricity, and that's this cost sigma here. This problem also allows us to look at questions of how do we, allows us to do some contingency analysis. So what happens if lines break, or if there's suddenly too much demand, a spike in demand? What is the effect on the power grid? Okay, there is a very nice and simple simplification. So we can look at a much simpler model. So I've talked about this really complex model, and very early on we said, make it as easy as possible. So we can simplify these AC power flow equations by simply using a Taylor approximation of sine and cosine, for example. And so this is really not very hard. So if I look, for example, at this would be sine of x, then around the origin, around this point here, sine of x is approximated very well by a linear function. So sine of x is approximated by x. And I can do the same thing for cosine of x. So I can draw a picture over here. So and again, near the origin, cosine of x is approximated well by just a constant 1. And if I do these simplifications and set V, the voltage magnitudes, to 1, then, oops, I wanted to go the other way. I can go into my power flow equations here, for example, and simplify them. They become a lot simpler now. If my V's are equal to 1, hey, I've removed my bilinear terms. The sine and the cosine, I just plug in. Either I make the cosine is just equal to 1, so that's just a constant. I'm just going to throw away that equation. And where I have a sine, I now have my balance equations here. And on the right-hand side, I just have some angles with a constant in front of it. So very simple. This is now a linear system of equations. Brilliant. That's what we want. So a question, of course, that you should ask is, how good are these linear approximations? So you can see that if you go too far away from the origin, this no longer looks like the sine function or the cosine function. And so we did a little bit of an experiment with this a long time ago. We looked at a problem of transmission network expansion. So you're given a network and you now build a new city, or you need to have more demand. There's a factory that's being built, so you need to, or another generator comes online, maybe renewable energy, so you need to expand your power system, your power grid. And the question then is, where do you put these additional lines? So we are going to introduce binary variables now, yik, to model this network expansion. So for all the existing nodes in my network, the yik is going to be set to 1, because I'm not going to destroy my network to build a new one. And there's a set of additional lines in the network. And then on those, I do my old trick. So I have my line flows, the piks and qiks, which are these complex expressions. And if I don't build a line, then these line flows are going to be 0. And if I build a line, then they're allowed to be between their usual lower and upper bounds. And what I want to do is then minimize something like load shedding or minimum investment cost. I really need to start using a spell checker. That's terrible. And that's the German way of spelling investment. So there you go. That's okay, mark that. Or maybe the cost of building these lines. And what we're going to do is we're going to compare a nonlinear AC model and a linear DC formulation. So we can run these two models, and what you get on a very simple network, we just have a very trivial network here where we allowed ourselves to build additional lines. We have the linear network expansion here and the nonlinear network expansion over there on the right. And what you see is that they look very different. So the network expansion solution that you get looks very different. And if you're planning, if you're a planner and you're building lines, which one should you take? I should add that we're allowed to add parallel lines here because we have capacity limits on the lines. So sometimes there are parallel power lines that go across the country, and that corresponds to those. Okay, so which one is correct? Well, what we can do is we can check whether this solution that we get here actually gives us a feasible point in our nonlinear model. So that's something we can check. We can make sure that whatever we compute here, regardless of what the objective is, we just want to make sure that this network topology has a solution. And it turns out that that's not always the case. I've gone the wrong way. There we go. So there's actually, you saw there's a big difference between these, even on a small network. And it turns out that in some cases, this linearized DC model, this simple model, is not feasible in the AC power flow, or we couldn't find feasible points by solving the power flow equations. And we suspect that the reason is that this DC model is really an approximation on phase angles that only works in a small neighborhood. But if you change the topology of your network, then likely these phase angles change dramatically because you're sort of routing in different ways. And so that means you want to go to angles that are very far away from where you have good approximations. And when you do that, you get errors. You're suddenly no longer on this curve. So it's not to say the DC model isn't useful. It's probably useful for quick planning if not much changes in your network. But if there are big changes, then you probably shouldn't use it. There are a lot of other mixed integer nonlinear optimization power flow problems. So one is the unit commitment problem. That's a planning problem that says which generators do I switch on and off. That's typically run sort of on a moving horizon, either with hourly or quarter-hourly intervals, because some of the generators take a long time to actually come online. There are some generators which are quick to start, like gas turbines, and others take a longer time to come online. Transmission switching is a problem that's identical to the problem that I just showed you, but instead of adding lines, you allow yourself to just open a line. Opening a line means you basically don't let any flow go through it. And why would you want to do that? Is there an electrical engineer in the audience? I should have asked this before I gave this talk. Is there an electrical engineer in the audience? Okay, good. Or you're not raising your hand. That's great. Thank you so much. You want to do that because you can actually influence how, by switching lines on and off, you can influence how the power distributes through the network. And so you can manipulate the power flow in the network, and you can do that sometimes to safeguard against some things. For example, if we have geomagnetic induced currents, then we may, and we know which way the magnetic field is organized, we may want to switch some of the lines off that go through these magnetic fields in a certain way so that they don't overload. Contingency analysis for blackout prevention. So this is a really challenging problem. As a generator or as a system operator, you have to show that when you're submitting a plan that it's safe to do so. And the way to do that is to say, you run contingencies that say, what happens if one of my lines fails? Can I still satisfy demand? And you have to do that for all the lines. Ideally, you want to do it for what happens if 2 out of all my lines fail and repeat. But these are very challenging problems that become exponentially hard to solve. And then I talked about the scheduling of black start generators. How do you restart the power grid? Once it's down, how do you restart it so that you get up and running as quickly as possible and satisfy as much demand as possible? And that happens a lot. So in the US, we have these things called snowstorms and polar vortices, and they have terrible effects on the power lines. They come down, they break, and then it takes sometimes days for people to get power back. Luckily, my neighbor has a little diesel generator, so we're not too affected by that. So here's just a picture of blackout prevention. This was the 2003 blackout. On the left is the eastern seaboard of the United States. So this is New York, Baltimore, Boston, and so on. On the right is what it looks like during the blackout, and so you see much fewer white there. And this costs between $4 and $10 billion. So solving these problems is really important. And currently we can do maybe 20 lines or so. We really want to do it on a much larger network. But these are very hard combinatorial problems. And then Steve Wright from the University of Washington has looked at ways of solving these problems where he sort of looks at a bi-level approach where he has an attacker that is allowed to decrease the line admittance to disrupt the network. So your attacker can impact the line admittance and can shut lines down. And the system operator then adjusts demand and generation to respond to this attacker. And what they found is that about 80% of the lines are not vulnerable to these attacks. So even if the attacker really degrades these lines, most of the lines don't have an impact on the power grid. So it's a very robust system in that sense. But 20% of the lines are vulnerable, and knowing which these lines are will probably help you to figure out how to build a better power grid, how to prevent this from happening, or hardening these lines. Okay, so I made it almost in time for coffee or tea. So AC power flow equations there, nonlinear, complex valued, complex variable equations, but that's not a big deal, right? You just have two copies of each variable, one real, one imaginary. There's a very, very rich set of applications, a lot of nonlinear optimization problems, mixed integer nonlinear optimization problems, games or leader-follower games, Nash-Go-No games that you can play. The DC linear approximation is of K if the settings in your network don't change. So and the reason is that this Taylor expansion that I did for cosine and sine is only valid in a small range of angle differences. But if you change the topology, these angles will change dramatically. And there are many applications for mixed integer nonlinear optimizations, adding binary variables to it. Something I haven't talked about is uncertainty. So one of the things that's very current at the moment is how do you deal with uncertain wind or uncertain solar in a system that's getting more and more reliant on renewable energy. So the US wants to move to renewable energy over the next decade or so, and that's going to create huge challenges if we don't know how to handle the uncertainty in the supply side of the power grid here. And Germany is already there. They're already very aggressively putting wind generators. I grew up in the north of Germany, and it's very different to what it was 20 years ago, even 2 years ago. The wind farms are just popping up all over the place. And there are also some people who put in solar plants, and I don't know why you put solar plants into Germany. The sun never shines there, but somebody does that. So this would make much more sense over here. Do you have any questions for me, other than why we put solar plants into Germany?
So these are which are, some of these are operating decisions at what voltages or capacity should generators run. And these have to be solved in relatively short period of timing.
Yeah. So no, so the expansion models, you have time, because those power lines they're built over decades. But for example, for the unit commitment, you probably need to solve that within 5-10 minutes or so. So, and maybe even faster if you do contingency analysis.
And then somebody has to say that the answer is reasonable.
Yeah, I don't know what happens there, but I think they don't like you to tinker with the power grid. I think there's safeguards there.
Usually the solution would not be too different from what it is operating at currently.
Maybe that's not entirely true. So, for example, when you have a lot of renewable energy, if clouds come over and you suddenly don't have solar, then that could change quite dramatically. And so then you need to have generators that can boot up really quickly. But the generators are typically not. You're not going to, shut down a nuclear plant. That's sort of a base load that's almost always there, I think.